Hi everyone! Today, for this video, we'll be looking at time series regression and some of the analyses that we can perform using SPSS. There are basically four main analyses that we are going to do, which are modeling trend, autocorrelation, seasonal variation, and growth curve model, which means I'll be dividing this video into four main parts as well. And for the last part, which is a growth curve model, one of my colleagues will be taking over. So the first analysis that we are going to do is the trend analysis, which means we are going to see if trend exists or not, and if it does, we want to know if it's a linear trend or a quadratic trend. For the second part, we are going to see if autocorrelation exists or not. And to do this, we are going to perform Darwin-Watson test. And for the last part is seasonal variation, where we are going to use dummy variables to forecast our data. I'll explain more detail once we get to those parts. But for now, I'm just going to show you like these are the data that we'll be using. So basically, it's a data of mean of carbon dioxide throughout the year from 1975 until 1980. So this is a monthly data. As you can see over here, they plot it like they have it for every month from the 1st January and then 1st of February, 1st of March until the very last one, which is the 1st of December. So that is about for a data for 5 years. So now let's proceed to the first part of this analysis. Okay, so for the first part of this analysis is we are going to see the trend for this data. So why I want to do this is because before I want to estimate time series using regression analysis, we have to estimate the type of trend first and see which one exists. Basically three types of trend. So no trend at all, linear trend, or quadratic trend. So what does it mean by no trend is the time series doesn't increase or decrease over time. So it just randomly fluctuates. And this trend equation later on is equal to a constant value, which is also the intercept of the regression equation. But for a linear trend, it means that the value of the time series tend to increase or decrease at a constant rate and thus produce a straight line. So the value of the time series for a t period of time equals to beta naught plus beta 1t plus error term in time period of t, which is equals to y equal to mx plus t. And there are also two types of linear trend, which is positive or negative. And positive means the independent variable increases at a constant rate over time. And for negative, it means that the independent variable decreases at a constant rate over time. And for a quadratic trend, it means that the value of the time series tend to increase or decrease at a rate that is not constant. And for a quadratic trend, we also have two types, which is positive and negative. So positive means that the value of yt, which is the time series in time period of t, increases at an increasing rate over time. And same goes for the vice versa. So now we are going to show how we can perform the analysis using SPSS. So first click Analyze, go to Regression, and click Curve Estimation. So as you can see here, make sure that for the dependent variable, we put the mean of carbon dioxide, and then for the independent variable, we put the variable t. And make sure that these two boxes are clicked, which is linear and quadratic, because we want to see later on which one of these two models exists for this data. We also want to click the display ANOVA table because we want to see the significance level. So we click OK. So first we will analyze for the linear trend. So if we see the ANOVA table over here, we can see that there is a significance value. So we just double click and we can see that the value is actually equals to 1.7146 times 10 power of negative 14, which is a very, very small number. So as we all know, for a 95% confidence interval for a hypothesis testing, if the p-value is above 0.05, this means that the null hypothesis can be rejected because there is not enough evidence to show that there is a trend in the data. But since this value is very close to 0, which is of course way below 0.05, this proves that the null hypothesis cannot be rejected, and there is enough evidence to show that there is a trend in the data. Since linear trend does exist, we want to see the coefficient for the linear trend, which is beta naught and beta 1. So these are the value. So this value shows that the value of the time series in time period of t equals to 330.354 plus 0.117 t. So moving on to the quadratic trend. As you can see here. Okay, the value that we want to see is this 3 value. Okay, we can see over here that the value for t is significant, which is equal to 0.086. But the value for t squared is very small and very close to 0, and thus making it not significant. So this shows that there is a quadratic trend does not exist for this data, but linear trend does exist. So therefore, for this data, we can forecast it with linear trend model. And we can also take a look at the graph here. Okay, as you can see here, there is a linear trend that is proved by this line here, and prove our conclusion before. Okay, so moving on to our next analysis is autocorrelation. As you all know that one of the assumptions in regression is that there is no autocorrelation exists between the error term, which means that each error term observation must not be correlated to one another and must be independent to one another. So if this assumption is not met or it's violated, it shows that the error terms are dependent to one another and concludes that autocorrelation exists. So when autocorrelation exists, this means that the error term observation actually follows a pattern and showing us that something is wrong with the model, since error term represents the distance between the actual value and predicted value. So there are 3 types of autocorrelation, which is the first one, positive autocorrelation. Negative autocorrelations are no correlation at all. So what it means by positive correlation is, so let's say there is a positive sign of error term. So positive autocorrelations means that the error term after it has the same sign. So if positive error term, it will followed by another positive error term, and it might followed by another positive error term. But for negative autocorrelations, it means that let's say we have positive error term, it immediately followed by the opposite sign, which is negative error term, and after that it follows by another positive error term. So it alternates. So for the most common situation for autocorrelation is actually, we call it first order autocorrelation. So this means that the error term in time period t is related to the error term immediately precedes it, which is in time period t minus 1. So this is what we're going to do for the Darwin-Watson test, because Darwin-Watson statistics is strictly for first order autocorrelation only. So for Darwin-Watson statistics, the statistic value ranges from 0 to 4. So the closer the statistic value to 0, this means that there is a higher tendency that positive autocorrelation exists, while the closer it is to 2, there is high likely that there is no autocorrelation at all, and the closer it is to 4, then the more likely negative first order autocorrelations to exist. So but the rule of thumb that you're going to follow is, if the test statistic value fall between 1.5 to 2.5, then that means no autocorrelations exist. Thus, if it falls outside of this range, that means either positive autocorrelation or negative autocorrelation exists. So let me show you how we can do the Darwin-Watson statistics using SPSS. So we click Analyze and go to the regression part, and we click Linear. So as you can see here, we put the dependent, for the dependent, the mean for the carbon dioxide, and for the independent, we put time t. So we click Statistic, and you have to make sure that this box here, which is the Darwin-Watson, is ticked. And we click continue, and we move on to the save. And because we want to plot a graph later on, so this we have to click this unstandardized under the residual box so that we have the value later on. So we click continue and we click OK. So what important for this test is this one. I'm gonna show you. Yeah, here. This is the value that we are looking for. So as you can see here, the value is 0.326. So like I mentioned before, this value is very close to 0, and that means that there is a positive autocorrelation. So to prove it, to double confirm it, we can plot a graph. So to do this, we go back to the main page, we put graph chart builder. Okay, so we can choose either one. So let's say I want to do scatter plot. So I just drag it here, and then we put the unstandardized residual that we just ticked just now, the value that we just got, and then we put it on the y-axis, and we put t on the x-axis. So we click OK. Yep, as you can see here, this is the line, right? This is the line. So as you can see here, this arrow term, have a positive correlation, because like this one, positive arrow term is immediately followed by another positive arrow term. So it moves like this. So this proves the value that we got just now, which is 0.326, and concludes that for this data, positive autocorrelation does exist. So for the last part of this analysis, we are going to see the seasonal variation, and we're going to forecast this data. So before we go any further, we want to see first if there's any seasonality exists or not for this data. So how we're going to do that is, first we just click graph, click chart builder, and click OK. Okay, I already put it here. So just click line and then drag this thing over here, and then make sure here is a mean of the carbon dioxide, and put T, which is the index, over here, and then we just click OK. So as you can see here, yeah, this is you can conclude that seasonality does exist, and there's actually two types of seasonality: constant and increasing seasonal variation. So but you can see here, since we have the index from 0 to 72, we can see that from here to here, it is a constant seasonal variation and not increasing, because you can see the constant of this of how this data look like. So there are two ways that we can analyze a time series, either using a dummy variable or trigonometric function. But dummy variable is strictly for constant seasonal variation, while trigonometric function is for both, which is constant and also increasing seasonal variation. But since the data that we have here is already constant, so we are just going to proceed with dummy variable. So the function of this dummy variable is to basically control the seasonal variation that happen throughout the year or throughout this data. And because it goes up and down throughout the year, we want to net out and average out the average change in the variable. So the general form of the estimated multiple regression equation for modeling both the monthly of this mean of carbon dioxide, seasonal effect, and the linear trend is y equals to b naught, beta naught plus beta 1 m1, beta 2 m2 plus beta 3 m3 plus beta 4 m4, and until the last one, and plus beta 12 t. So y here is basically the value that we want to forecast, the value that we want to get. So since we have beta naught until beta 12, right? And we also have M1, M2, M3 until M11. So what we can see here is that M1, M2, and until M11 are the dummy variables. So we have until M11. So that means we have, those are the dummy variables basically. So M1, M2, M3. So this is basically the Excel, because we have to do this thing in Excel. I cannot do it in SPSS. So the general rule of thumb is, if you have a categorical variable and you have k level of it, so that means that you need to have k minus 1 dummy variables. So since this is a monthly data, so that means we have 12 months, right? That means we need 11 dummy variables, which is shown here from M1 until M11. So this dummy variable is coded as, let's say for M1, right? So how are we going to fill up all these cells is basically, there are like some 2 or 3 ways that you can do it. One, you can just do it manually, or you can just do it using if function. So basically what we do here is, if you can see here, if C2 is basically the month. So this is M1, right? So if the cell over here is equals to 1, which is January basically, right? Then the cell here should be 1, equals to 1. But if it anything else, then it should be 0. So only here is the value of 1, but all this until the 12th one equals to 0. And then we just continue doing it until the very last year, since we have 1 until 12, and then we repeat it from another 1 until 12. And we also do it horizontally. As you can see here, 1, 1, 1, 1, 1 until here, and then it basically repeats until the very last year, until here. So basically we use Excel because we just want to fill up this cell. Once we already done this work, we can just proceed with SPSS, where we import this data to SPSS. But I already put it here, yeah. So we're good to go. So now why we have this dummy variable is basically because we want to forecast, right? And since, like I mentioned before, from the equation we have beta naught plus beta 1 M1 plus beta 2 M2 until the very last one, which is plus beta 12T. So we use this dummy variable to basically to get the value of the betas, to get the value of the coefficient. And when we have this value of the coefficient, then only we can proceed with forecasting, where we can just forecast to whatever period that we want. So basically what you should do is, first we go to analyze, and then go to regression, and then click linear. So we have mean carbon dioxide right here. We put it in the dependent box, and then for the independent box we put T until the very last one, which is M11. So that is all. You don't have to alter anything else, and just click OK. So these are the values. Okay, I'm going to highlight it. So these are the value that is important for this analysis. So basically these are all the value of the betas that we mentioned before. So this is for beta naught, and then this is for beta 1, beta 2, beta 3, until beta 11. And now, since we already finish figure out the value of betas, we can just proceed with forecasting. So there are basically like 2 ways you can do it. So since we already fill up this equation, you can just do it manually. If you can see here, the very last data is the index 72, right, which is here. So let's say we want to forecast for the next year, for the next 1 whole year. So the value here will be 73, right? So, and then you can just proceed with a value of 1, 0, 0, 0, and then 0, 1, 0, 0, 0, and then put it inside the equation, since we already have the beta. So now we don't have any other unknown variables. And then for the last part, which is plus beta 12T, the value T here is basically the value of T over here, which is if you want to forecast for this cell right here, which is a 73, we just put 73 in the equation. So now, since all the variables have been filled up, we can get the value of y, which is, like I mentioned before, the forecasted value that we want to see. So if you want to see like the graph of for this forecasting, you can just easily do it by click analyze here, and then click forecasting, and then click create traditional models. Okay, so basically what we're going to do is make sure for the dependent variable we put a mean of carbon dioxide over here, and then proceed to clicking this display forecast because we want to see the forecasting, and go to save, and then click all these three boxes because these are the values that we want to see in the output. And last is a very important one, which is the forecast period. So the this first case is basically the value that we like, so from the initial value that you already set before before we forecasting. So the first case is basically the first year and the first month with it, which is January of 1975, and then end of estimation period to until this year. So because this data ends at 1980, so we want to forecast for another 2 years, which is until 1982, and the very last month would be December. So there are basically 24 months altogether, and then you just click OK. So as you can see here, the data ends over here. This is December of 1980, and then basically what it just did is forecast for another 2 years until December 1982.
Growth curve model can be used to forecast time series data that exhibits an exponential pattern. However, this model is nonlinear in parameters. Thus, the parameters are transformed to obtain a linear model or equation that is representative of the time series data. By doing so, we can easily estimate the parameters required to conduct a forecast and interpret the data as a whole. For example, we can use the estimated growth model to estimate the value of a particular variable in the future and obtain the point estimate of growth rate. The point estimate of growth rate gives us information regarding the increase or decrease in the value of a particular variable after a certain period of time.
Next, we will show how to perform the growth curve model analysis by using an example. In this Excel worksheet, we have a time series data that shows the number of reported cases of a new disease over the last 11 months. T represents the time in months and YT represents the number of reported cases, while in the third column, we have the natural logarithm of YT. We are going to use SPSS to conduct the analysis. Before we can use SPSS to perform analysis, we need to read the Excel file using SPSS to import the data required. Click File, Open, and then Data. Since the Excel file is saved in the desktop folder, look for it in that folder and then choose the Excel file type. And choose the number of reported cases. Finally, click Open and click OK. Go to the Variable View panel to make some adjustment. Change the decimal section to 5 for long YT and make sure all the measures are in scale category. Next, we are going to plot graph for YT against T. For that, go to the Graphs, Legacy Dialogs and choose Line. Click Define. Insert the variable T as the category axis. Click Other Statistics, YT and insert it as variable. And click OK. So, the output window shows the graph. Next, modify the axis title and the graph titles accordingly. So this is the finalized graph. As we can see, the graph of YT against T is exponentially increasing and non-linear. Thus, we need to take the natural logarithm of YT to obtain a linear plot. So to plot the graph of long YT against T, we repeat the similar procedure. Remove variable YT and insert variable long YT. Click OK. And this is the graph in the output window, and again make appropriate adjustment. The graph of ln yt against t is linear, therefore we can use least square estimate to model the data. The exponential plot suggests an original model of yt equals to beta naught times beta 1 to the power of t times epsilon t. After taking the natural logarithm, we have ln yt equals to alpha naught plus alpha 1 t plus mu t as the model, where alpha naught is equals to ln beta naught, alpha 1 is equals to ln beta 1, and mu t is equals to ln epsilon t. In order to regress ln yt against t, go to Analyze, Regression, and choose Linear. Insert t as the independent variable and ln yt as the dependent variable. Go to Statistics, make sure to tick Estimates and Model Fit, and then click OK. As we can see, the output window, and click Coefficient. We obtain alpha naught hat equals to negative 0.543 and alpha hat 1 equals to 0.390. Thus, we can estimate ln yt as ln y hat t equals to negative 0.543 plus 0.390t, where now we know that ln yt is approximately equals to negative 0.543 when t equals to 0, and for an increase in month, the value of ln yt increases approximately by 0.390. Our aim here is to forecast the point estimate and prediction interval for the next 11 months. For that, go to the Data View tab and key in 12 to 22 in the month column. After that, go to Analyze, Regression, Linear, click Save, tick Unstandardized under Predicted Values and Individual under Prediction Interval, click Continue and OK to obtain output. Go to the Data View tab. The column labeled pre_1 gives point estimate for each month. The column LICI_1 gives the lower limit of the predicted intervals, while the next column gives the upper limit of the predicted intervals of ln yt. Since we are interested in the point estimate and prediction interval of yt, the number of reported cases, we need the exponential value of the last three columns. For that, go to Transform, Compute Variable, insert title of target variable, in this case point prediction of yt, and insert the numeric expression as shown. Do the same for the other last two columns. Go to the Data View tab to see the results. For example, the point estimate of yt for month 12 is 62.57 cases, while the prediction interval of yt for the month is 46.08, 84.97. This can be interpreted in such manner. The estimated number of reported cases for month 12 is 62.57 cases, approximately 63 cases. As for the prediction interval, the number of reported cases will be at least 46.08 cases and at most 84.97 cases for month 12. This follows the rest of the months. Next, using the value of alpha hat 1, we can obtain the value of beta hat 1. Go to Excel, select a cell to insert the value of alpha hat 1, which is 0.39. And this alpha hat 1 is equals to ln beta hat 1. To obtain the value of beta hat 1, simply apply the exponential function to alpha hat 1, as shown. Now, we can obtain the point estimate of growth rate. Take the value of beta hat 1 and minus by 1. Next, format the cell into percentage. Right-click the cell, go to Format Cells, choose percentage and limit to 2 decimal places, and click OK. Thus, the point estimate of growth rate is 47.70%, which implies that the number of reported cases grow by 47.70% from one month to another. And that's all for growth curve model.